Hey everybody, welcome to another problem. And in this problem, this problem comes to us as usual. In recent times, I've been doing problems from the JEE 2020. It's a paper one. So let's look at this problem. This actually is an interesting problem. It's a good physics problem, and it comes from the electric current part of your chapter. So you need to know electric current, Ohm's law, maybe conductance, you also maybe need to know some, I think down here you need to know like current density, J, like J times area is current, that formula. And you need to know for doing this part, the last part, you will have to kind of make some assumptions, some physically reasonable assumptions. Okay, so let's do this problem. You have a semicircular and the thickness is not shown here. So there is a thickness to this thing. It's kind of like thickness. If you're looking at another angle, you would see the other thing, but this is cross section. This thickness is T. And the current just goes and spreads out, and that's why you need the okay. So there's a voltage that sets up between this inner edge, and similarly there's the outer edge behind here. So that's the outer edge. Okay, that voltage is delta V, and we're supposed to ignore, not worry about magnetic field that will be generated by these currents. Just electrostatics kind of stuff, or not like, yeah, it is statics. Electric field will be not changing in time. Okay, so let's do this. How do you figure out that this current I that flows through this is equal to that? And so we're supposed, so over here resistance is 0, this is resistance is 0, this line is just line, this is 0, so all the resistance must be coming from here. So to show this, we can do this like I over V0. V0 is the voltage. Look at equivalent. So the resistance of this whole thing will be inverse of this. This is T over pi rho log R2 over R1. So this is like 1 over resistance equals to conductance. That was saying conductance. So V equals IR. So this 1 over resistance. So we have to show the conductance has this formula. So if you look at a little piece, so we look at let's look at this. So its distance r and thickness dr. So what will be, you have a wire that long, of course you can stretch it out and make sure what you know. So the length will be this will be pi r, and the area of cross section area will be t, t this way, dr that way. So G is the conductance, then dg for this little piece, infinite piece, will be equal to 1 over resistivity times it will be area over length. This is exactly inverse of the conductance. So this will be 1 over rho pi r t dr. So I just have to integrate this. This will be, we check that's the formula or not, this G, and this whole thing becomes T over rho pi R1, R goes from R1 to R2, R1 to R2, dr over R, and this is T over pi rho log R2 over R1, and that is correct. That's what that is. So this is correct. So A is correct. Now B and C says, is this side positive or this side positive? So B is saying that this is positive and this edge is negative. C is saying the outer edge is at lower voltage. So C is saying that this is negative and this side is positive. Okay, so this is really not that difficult to answer, because we can take one at a time. If it's positive, it's negative, and the electron, if the current is going this way, the electron is going that way, and it's going in a circular motion. So we need a force, we need an inward force for this motion to be circular motion like that. So we need force this way. So if it's positive is negative, so that will create a force that way for the B. That's the opposite. Is C, then the force will be that way for C, and that's the force direction we need. So this is C is correct, B is not correct. Now how do we solve this? Well, we are going to some kind of averaging, average thinking. So say you had two plates. This is the R1 surface plate, and this is R2 surface plate, and you had positive this guys, and this negative this guys. Then if the voltage difference between them was delta V, then you'll say the electric field is delta V over R2 minus R1. That's the distance. So this is electric field, and what do we have? Charge, any charge in the middle, any charge times the electric field. That's the force. It's going to be mass of the electron v square over r, say over here. Okay. So what should we use for r? We're going to focus on, say, halfway. So let's call this R1, R2 minus R1 over 2. So that's average effect we're going to, because we're just looking for dependence, right? So we're not looking for exact, so we're just going to focus on, there are other ways of solving this problem, but this is a good enough hand-wavy way. So bring this on the other side, 2e R2 minus R1 E, and that just can turn out to be delta V. This E over 2, not 2E, E over 2. And that's just going to be ME N square E square NeV. N is the number of conduction electrons per volume, per unit volume. So this is going to be square, and that's going to be J. So mass of the electron, let's just M, not Me, N square E square J square. Now J times the area of cross section, the entire area of cross section is T times R2 minus R1 equals to the current. So we can just square it. So you have a delta V on this side, get E on the other side, M, and multiply and divide by this, so they convert to I square, M or N square EQ T square R2 minus R1 square, and then the whole thing becomes I square. So delta V is proportional to I square. That turns out to be correct. All of this is constant, same thing, doesn't depend on I or V. So this is also correct. So for this problem, the answer would have been A and C and D, and B would be incorrect. Those are the answers. Okay, it was an interesting problem. I will see you another problem. Bye.